So my brief lecture today from differential geometry is going to be about mapping, the tangent map, and the Jacobian. And of course when I say mapping, I mean a function from n-dimensional space to m-dimensional space, and we can represent that function with the coordinates f1 through fm, where really, if you think about it, f of x1 through xn, it's going to be just f1 of x1 through xn, f2 of x1 through xn, all the way down to fm of x1 through xn. And each of these f's of j, where j go from 1 through m, is just going to be a function itself from Rn to Rm. So let's talk about the tangent map of that mapping from Rn to Rm. We're going to represent the tangent map by f sub star. It's going to map the tangent space of Rn at the point P to the tangent space of Rm at the point f of P. So really the tangent map of some tangent vector at P is just going to be f sub star v sub P, and it's really going to be v sub P bracket f1, v sub P bracket f2 down to v sub P bracket fm, and it's going to be an m component vector anchored at f sub P. We can call it w of f sub P. So really all it's doing is just taking the directional derivative of each of my Euclidean coordinate functions in the direction of the vector v anchored at the point P. Now let's talk about frame fields. My frame fields for Rn is just going to be u1 through un, and the frame fields for Rm with a little bit of abusive notation is just going to be u1 through u sub m. Okay, and it turns out that the ith frame vector field applied to the jth Euclidean coordinate function is just going to be the partial f of j with respect to xi, where of course the j goes from 1 through m, the I goes from 1 through n. In particular, since a frame field is also a vector in a sense, we can say the tangent map on u sub I is just going to be the partial of f1 with respect to xi all the way down to the partial f of m with respect to xi. Now suppose we just take a tangent vector, we can rewrite it as a linear combination of the vector components of v multiplied by the respective frame field, vector field. So when I apply the tangent map to v, what I'm really getting then is the tangent map applied to v written as a linear combination of the frame, the corresponding frame field. And since the tangent map is linear, it's a linear mapping, it's just going to be summation I go from 1 to n to v sub I f star u sub I. But it turns out the f star u sub I, if you recall correctly, that's just going to be the partial of your f sub j with respect to x sub I, where j goes from 1 to m. Okay, u sub j. But then we can write all this, since I got i's and j's in matrix notation. My m by n matrix, the first row is just going to be the partial of f1 with respect to x1 through the partial of f1 with respect to xn, and the nth row is going to be the partial of the nth Euclidean coordinate function with respect to x1 all the way down to the partial of the nth Euclidean coordinate function with respect to xn multiplied by the vector v. Well, this matrix on the left has a particular name. It's called the Jacobian of my mapping big F from Rn to Rm. And so we can do some matrix notation and really say that the F star V is really just the Jacobian of F dotted with V. Or if you want to write it matrix notation, it's just be in the matrix notation partial F sub j with respect to xi sub ij multiplied by the column vector v1 to vn. Okay, so really then your tangent map applied to a tangent vector in Rn becomes a Jacobian of that map dotted with that vector. Just like when you were studying a mapping, say f from r cubed to r, and you want a directional derivative of that mapping f from RQ to R, it turned out to be the gradient of f dotted with v. So in a similar sense, now that we have taken n-dimensional space to m-dimensional space, we're going to get the Jacobian of f dotted with v, or just in matrix notation, the Jacobian f multiplied by the vector v. Funny how all this notation comes down to some elegant representation. I hope you got a good understanding of mappings and what we can do with them in order to understand their dynamics through messing with directional derivatives and going through the Jacobian. Have a beautiful day. Think about these things, because the differential geometry of n-dimensional space is really beautiful. Voila.